Alrighty, so this is our PowerPoint presentation. Our group name is the P2BG, and this is December 3rd, 2012. For our design of experiments, we chose to check out the fizziness of soda. Our group, this is our group. I'm Nolan Power.
I'm Ethan Beyak.
I'm Huilong Gao.
I'm Kevin Barr.
And that's our group P2BG. For our experiment, we chose the fizziness of soda. Why did we choose this experiment? I had lots of Sprite and Kevin had Dr. Pepper, and I don't particularly like fizziness in my soda, so we decided to check out which one were fizzier. What we found was the height of fizz of these sodas. Dr. Pepper, which was our positive, and Sprite, which was our negative. There was 3 different variables with 2 different levels. 21 degrees Celsius was our positive and versus our 3.9 degrees Celsius, which is our negative. And we had 2 different heights, which was 9 inches, our positive, versus 7 inches, our negative. And this was measured from the bottom of the cup. For our procedure, step 1 was we would take the temperatures of the different sodas to make sure that we had the right temperature for when we were pouring.
For the step 2, we measure out the half of a cup of the Sprite and the Dr. Pepper. For the step 3, we poured the soda into a temperature-sensitive cup at various heights. And after that, for the step 4, we measured the height of the fizz.
For step 5, we compared the height of the fizz to the height of the soda to find the height of the fizz together. Our results were that the Dr. Pepper at the cooler temperature poured from the higher height of 9 inches was the fizziest, and it had an average of 1.04 inches of fizz, and our combination that was had the least fizz was Dr. Pepper at the cooler temperature poured from a height of 7 inches. This showed that the brand didn't have much of an effect on fizziness. This is our complete matrix. As you can see, we have the way we did our experiment, and you can see under our A, B, A, C, B, C columns that you have positive interaction between brand and temperature, same with temperature and height, and as well with temperature and brand.
Now, further analysis of this experiment shows that the most significant factor is the height from which we poured the soda, which was the 9 inches and the 7 inches from the bottom of the cup, which was a 5-inch tall cup, by the way. And 2 other important factors were the interaction between the brand and the temperature, and the interaction between the temperature and the height. Now, if we go to our predictive equation as discussed in the DOE textbook online, we have the following setup in variables for a 3-factor 2-level experiment. Now, with our beta naught, what we had to do is take the average of every single average. So what does that mean? If we took our 8 trials for one of our combinations, let's say Sprite at a low temperature at a low height, we had to do that 8 times, and then what we did, we averaged all of those 8 trials. So we did that for every single combination, and we had 8 combinations. So we had to take the average of all the averages, and that is our beta naught. Now, as we move on, our x1, which was our first factor, we said our A was the brand of soda. And if we look at the coefficient, or the beta 1, the coefficient was 0.05, and in comparison with the other coefficients, that is not that significant. And as we move on, our x2 was our B, which was the temperature. That was somewhat significant, but not the most. It looks like it's the 4th. And then for x3, C, that is the height. That is a 0.18, and that is by far the largest coefficient, so therefore the most significant. And then here we get the X1, X2 term, which is the AB, the interaction between the brand and the temperature. That was the second most significant. And then we move on to the X1, X3 term, which was 0.04, the interaction between the brand and the height. This was surprisingly very, very small. So that is almost negligible. And as we move on to the interaction between the temperature and the height from which we poured the soda, that was the third most significant at a 0.13. And as expected from the DOE textbook, they said that the interactions between all of the factors in a 3-factor 2-level experiment should be the lowest, or one of the lowest, and it is. It's a 0.06, which is the third lowest. Now, as we move on to the recommendations of further research, we looked at several uncontrollable variables in our experiment. For example, we had a constant velocity problem. Now, if you know just from experience with soda, if you pour it slowly, then there won't be much fizz that will be produced, because there isn't enough energy to excite the carbon dioxide in the soda to get it going from a liquid state to a gaseous state, in broad terms. So what we had to kind of ameliorate that problem, we had Kevin, the master pourer, he consistently poured every single time, and it appeared like he was pouring at the same velocity, roughly. Now, of course, roughly isn't that technical and precise, but it's the best we could do. Some options that we thought of to solve this problem was we had the idea that we could turn the soda bottle upside down onto some sort of solid block or a board, and then like a magician pulling out a tablecloth, we would move the solid board, thus having the soda pour out of the bottle due to gravity alone. It wouldn't have to deal with our hand motions and movements. So that was one idea, but then we thought about it more, and the act of taking away the board would probably get soda everywhere, and that would disturb our results and get unwanted soda everywhere, having to clean it up and such. Another uncontrollable variable was the air density. Now, sure, this is probably negligible, but it would be good just to know the air density in the environment in which we are performing the experiment. For example, if we did it outside, it would probably be a different air density than in a controlled lab or in a dormitory, for example. And another uncontrollable variable we had was soda becoming flat. As we did our trials, and with our first one, we had just opened the soda bottle, so the soda wasn't that flat at all. But as we got to the 7th and 8th trial, the bottle had been open for about 5 minutes or so. And during those 5 minutes, it most likely got a little bit flat, if not more than a little bit flat. So the way to get around this problem would be to have small little soda bottles for every single trial, for every single combination. Now, as you can imagine, this would get expensive quite very quickly. With 8 small little bottles for every single 8 combination, that's 64 if I can do my math. So as we go on, we see that the flatness is just kind of, it has to be there under a conservative budget of a college freshman. Now, also, we had the uncontrollable variables of different batches of sodas. As discussed in the DOE, you had the blocking of different batches. Well, here what we had different bottles of soda from possibly very different environments. For example, the sugar content in one Sprite can could have been different from the sugar content of another can. Now, this is unlikely since Sprite mass produces these things and they're probably very similar, but there might have been a small difference. And to work around this, ideally we would have had one big can, which would have had all the same consistency throughout. And lastly, to add on to our experiment, we would observe differences in, say, sugar content, caffeine, calories, just nutrition in general of the soda. So maybe for another experiment we could do Diet Dr. Pepper and Dr. Pepper, see the differences. Or we could do a very sugary Jones soda and compare it to maybe even a carbonated lemonade or something like that. So those were all of our uncontrollable variables. So thank you for listening. This is P2BG signing out.